In the previous lessons, we defined three coordinate systems: Cartesian, cylindrical, and spherical. We wrote the position vector and the differential elements in each system. In this lesson, we bring these systems together. We will discuss scale factors and how to remember them easily. Then, we derive the transformation matrices that convert unit vectors from one system to another. Finally, we work through examples, including cases where unit vectors from different coordinate systems appear in the same expression. Scale factors, or metric coefficients, tell us how much actual distance changes per unit change in a coordinate. In Cartesian coordinates, all three scale factors are 1. hx equals 1, hy equals 1, hz equals 1. This is because x, y, z directly measure distance. In cylindrical coordinates, h rho equals 1 and hz equals 1, but h phi equals rho. In spherical coordinates, hr equals 1, h theta equals r, and h phi equals r sine theta. Here is a useful mnemonic to remember these. When we move from one coordinate system to the next, the new length coordinate that did not exist in the previous system gives the scale factor for the corresponding new angle. Going from Cartesian to cylindrical, rho is the new length coordinate. So h phi, the scale factor of the new angle phi, equals rho. Going from cylindrical to spherical, r is the new length coordinate. So h theta, the scale factor of the new angle theta, equals r. For h phi in spherical, recall the right triangle relating r, rho, and theta. Rho equals r sine theta. Since h phi was rho in cylindrical, in spherical it becomes r sine theta. This mnemonic is not blind memorization. It comes from understanding the geometric relationships between the systems. Now, let us derive the transformation matrix between Cartesian and cylindrical coordinates. The general formula for a unit vector is E hat I equals 1 over hi, partial r over partial qi. Here r is the position vector and qi is the ith coordinate. We start by writing the position vector in cylindrical terms. R equals rho cosine phi e hat x plus rho sine phi e hat y plus z e hat z. To find e hat rho, we take the partial derivative of r with respect to rho and divide by h rho, which is 1. This gives e hat rho equals cosine phi e hat x plus sine phi e hat y. To find e hat phi, we take the partial derivative of r with respect to phi and divide by h phi, which is rho. The rho terms cancel, giving e hat phi equals minus sine phi e hat x plus cosine phi e hat y. And e hat z remains e hat z. We can write this as a matrix equation. The first row is cosine phi, sine phi, 0. The second row is minus sine phi, cosine phi, 0. The third row is 0, 0, 1. The key insight: do not memorize this matrix. Instead, remember the derivation formula and you can reconstruct it anytime. For spherical coordinates, we write the position vector as r equals r sine theta cosine phi e hat x plus r sine theta sine phi e hat y plus r cosine theta e hat z. Applying the same formula, e hat r equals sine theta cosine phi e hat x plus sine theta sine phi e hat y plus cosine theta e hat z. E hat theta equals cosine theta cosine phi e hat x plus cosine theta sine phi e hat y minus sine theta e hat z. E hat phi equals minus sine phi e hat x plus cosine phi e hat y. This gives the spherical to Cartesian transformation matrix. Now here is a powerful trick. These transformation matrices are orthogonal. This means the inverse is simply the transpose. To go from Cartesian back to cylindrical or spherical, just transpose the matrix. Swap rows and columns. And to convert between cylindrical and spherical, go through Cartesian as an intermediate step. First convert to Cartesian, then convert to the target system. With just these two matrices and their transposes, you can transform between any pair of coordinate systems. Let us work through two examples. Example 1. Express e hat x plus e hat y in cylindrical coordinates. We need the inverse transformation, so we use the transpose. From the transpose, e hat x equals cosine phi e hat rho minus sine phi e hat phi, and e hat y equals sine phi e hat rho plus cosine phi e hat phi. Adding them, e hat x plus e hat y equals cosine phi plus sine phi times e hat rho plus cosine phi minus sine phi times e hat phi. Example 2. Express e hat rho plus e hat theta in Cartesian coordinates. This is interesting because e hat rho is cylindrical and e hat theta is spherical. They come from different systems. The approach: convert each to Cartesian separately. E hat rho equals cosine phi e hat x plus sine phi e hat y. E hat theta equals cosine theta cosine phi e hat x plus cosine theta sine phi e hat y minus sine theta e hat z. Adding these, the result is 1 plus cosine theta times cosine phi e hat x plus 1 plus cosine theta times sine phi e hat y minus sine theta e hat z. The key lesson: when you have unit vectors from different systems in the same expression, convert each one to Cartesian first, then combine. Let us review. Scale factors tell us the actual distance per unit coordinate change. Remember, the new length coordinate in each system gives the scale factor for the corresponding new angle. The transformation formula E hat I equals 1 over hi partial r over partial qi lets you derive any transformation matrix from scratch. The inverse transformation is simply the transpose. To convert between cylindrical and spherical, go through Cartesian. With these tools, you can freely move between all three coordinate systems, which is essential for electromagnetic theory.